Proof by contrapositive is not a very difficult technique, and it's one that starts with the definition of what a contrapositive is. So if I'm going to start with that, you need to know that contrapositive is a proof style where if you have a statement that's if P, then Q. Like if I walk into a lion's den, then I will get eaten. Then I can say if not Q, then not P. If I am never eaten, then I can't possibly walk into a lion's den. Those kind of things. So it takes a little bit of brain finagling to accept it, but once you do, it's pretty obvious. And the way you prove it is you assume not Q, and you show not P. And if you assume that not Q means not P, then you assume that if P, then Q. So that's the essence behind contrapositive. I want you to look at this example. This is kind of just a simple one. If it is raining, then the grass is wet. Switches around to if the grass is not wet, then it is not raining. And as an example, the contrapositive of any true proposition is also true. So if we prove the contrapositive, we can prove the original truth. So here's an example of a word I have to define in order to do a theorem. I want to talk about the parity. X, Y are elements of the integers, and X and Y have the same parity. If they are both even or both odd. Parity refers to evenness. And the specifics of why I actually did a longer definition is because for even numbers, x is even if x is equal to 2k for some k that's an integer. And for odd numbers, we can say y, just to give a different one, y is odd if y is equal to 2 times a number plus 1 or minus 1. Actually, we'll just do minus 1 because that tends to be used more, but it obviously doesn't matter. Sorry, I'm getting used to my new sensitivity for this pen. There we go. So that should help you kind of with the proofs of some of this stuff that we're going to do. So, theorem. X and y are integers. If x plus y is even, then x and y have the same parity. This is a statement that I wish my freshmen had a better concept of. If you add two numbers up and it happens to be even, then they both have to be even or they both have to be odd. We start a proof by contrapositive by writing the contrapositive statement so we can prove that. If x and y have opposite parity, and that's more of a specific statement than saying they have the same or they have different parity, because there are only two possibilities. So if x and y have opposite parity, then x plus y is odd. This is actually a little bit easier to prove. So another thing I'm going to write is this statement without loss of generality, which is abbreviated in math terms W log. Without loss of generality, let x equal 2k and let y equal 2m plus 1. For some k, that's an element of the integers, and for some m, that's an element of the integers. Now, what does without loss of generality mean here? It means that x and y could be switched, that I could have the y equal to the 2k and the x equal to 2m plus l. If I don't write without loss of generality, then I actually have to prove this twice, even though that seems obvious to you in a proof. This is just the way of saying x plus y is equal to y plus x, and I can just call one 1 and call the other one and not worry about which one's which. think about statements that wouldn't be without loss of generality. If I had 2x plus y is odd, then I'd have to prove it either way. So this is, again, just a way to kind of take care of that. If I have x plus y and I have that equal to a 2k plus a 2m plus 1, this now is a very easy proof. I pull out the 2, k plus m plus 1. So 2 times an integer plus 1, which this is odd. And we can just put a little box, thus it is shown, because we've now proved that if they have opposite parity, then they're odd, which means we've actually proved that if x and y is even, then x and y have the same parity. So that's done. Okay. Another definition. These are not definitions of things you don't know. These are the mathematical ways to describe them. N is a perfect square if there exists a k in Z such that n is equal to k squared, using the math symbols here. In fact, let me kind of fix these a little bit. That's not quite as good. Okay, I'm done. Sorry. Getting distracted. N is a perfect square if there exists a k in Z such that n is equal to k squared. Okay. Another definition, a more strange one that we've alluded to a few times. This is the definition of modular arithmetic. This is one of my favorite topics that I wish I could do more with. And I spelled arithmetic wrong, sorry. Arithmetic. In modular arithmetic, mathematically means that for n and m that are elements of the natural numbers, remember the natural numbers are the counting numbers, 1, 2, 3, 4, 5, 6, 7, n mod m equals r is the remainder of n over m. So some examples of this are to say things like 5 mod 4. So I want you guys to think about 5 as the number, and then mod 4 is the description. Mod 4 means that we're going to look at what the number 5 is, but we're going to reduce that mod 4. Well, if I were to take that, I would take the remainder of 5 divided by 4. And the remainder of 5 divided by 4 is 1. So if I'm looking at mod 4 world, then my numbers 1, 2, 3, 4, 5, 6, 7, 8, they get transposed into just a cycle of 4. 0, 1, 2, 3, and then we kind of head back to 0, 1, 2, 3, 0, 1, and it just keeps going. Basically, we only have 4 numbers, 1, 2, 3, and 0. And that's mod 4. You guys have seen this before with the powers of I. If I have I to the 127, I know that that's equal to I to the, well, I look to see what's the multiple of 24 that's before 27, that's 3. This would be equal to I to the third, because if I divided 127 by 4, I'd get a remainder of 3. And by the way, that is equal to -1. But my point there is you've seen modular arithmetic before. If I do 100 mod 26, and I want to know what's the remainder if I divided 100 by 26, well, 26 times 3 gives me 78. Wait. My brain's kind of hurting here. No, I was right, 78. I just had it wrong on my key. And 78, so let's see, 78 is going to be the same as, it's 22 away, so this would be 22. Is that right? Yep. Because basically what I'm cycling down to is I'm saying, well, 78 restarts the cycle, and then I'm just 22 away. Let's do another one. Let's do 1001 mod 1000. As you might predict, that's just equal to 1. So modular arithmetic is used a lot in programming. It's used a lot when you just need a cycle of numbers kind of way down the thing just to know where it was in a particular cycle of whatever you are. And that's the mod you're in, what size cycle you have. So the theorem we're going to try to prove with this concept, and you'll see the concept of modular arithmetic, is that if n is a positive number, or sorry, positive integer, such that n mod 4 is 2 or 3, then n is not a perfect square. This is a very interesting property, and this goes into the concept of number theory, the study of the number line, the study of integers in the number line, specifically the natural numbers. And if you look at what n mod 4 is 2 or 3 means, it's that if you have a multiple of 4 and you add 2 or you add 3, you definitely don't have a perfect square. That's fascinating to me. Let's look at an example of that. If I look at a number that's multiplied by 4, like the number 328, I know for sure that 330 and 331 will never be perfect squares. And this is true for any of these. Well, because this is proof by contrapositive, and this would be a logical way to use contrapositive, I want to look not at those cases, but I want to look at the other case. If n is a perfect square, then n mod 4 is 0 or 1. Now that's even more fascinating to me than the other one. Now I'm saying that if I have a perfect square, it is definitely 0 or 1 mod 4. It's either a multiple of 4 or it's one more than a multiple of 4. In fact, let's put that in parentheses. Perfect squares are either multiples of 4 or one more than a multiple of 4. And you can start to reason through in your head that if your perfect square is from an even number, it would have to be a multiple of 4. And if it's from an odd number, well, you can kind of get down into those cases. So, part of the proof of this, we're going to start with this n. We want let n equal k squared, because that was the definition of a perfect square. And so we have this k that we're introducing for some k that's an element of the natural numbers. And we're going to look at 4 cases for what k can be, 4 mutually exclusive cases for that original number. And I just said that number could be a multiple of 4, and if it's a multiple of 4, then or multiple of 2, then it definitely makes sense that if you square it, it's going to be a multiple of 4. So 4 cases, and these are mutually exclusive, which means they can occur at the same time. And these are all inclusive, meaning it must be one of these possibilities. So these 4 mutually exclusive cases for k means that we have case 1 where if k is equal to 0 mod 4, which means that k is a multiple of 4. Well, that's intuitive enough, but let's just mean that if it's k is equal to mod 4, then k is equal to 4 times a number for some q that's an element of the integers. Actually, it's an element of the natural numbers. I know I'm being inconsistent with that, but that's okay. If k is equal to 4q, then n is equal to k squared is equal to 16q squared, which is equal to 4 times some 4q squared, which is definitely equal to 0 mod 4. So that's a check there for that one. Then we have if k is equal to 2 would be easy, but let's go ahead and do 1 mod 4. Then we know that k is equal to 4 times a number plus 1. It's one more than a multiple of 4. And then we know that n is equal to 4q plus 1 squared, or 16q squared plus 8q plus 1, or 4 times 4q squared plus 2q plus 1. So 4 times a number plus 1, which means it's 1 mod 4. Once you get the rest of these going, you can see how this is going to play out, but let's finish it. If k is equal to 2 mod 4, then k is equal to 4q plus 2. And n is equal to 4q plus 2 squared, which kind of an easy way to do that without multiplying it all out is just to square the 2. Basically, you factor the 2 out of the 2q plus 2. Sorry, plus 1, my bad. Squared, and then square the 2, so you get 4 times the quantity 2q plus 1 squared. So just 4 times something, which is 0 mod 4. And then lastly, we have k is equal to 3 mod 4, or k is equal to some 4q plus 3. So then n is equal to 4q plus 3 squared, no factoring trick there, so let's multiply it out. 16q squared plus, let's see, that would be 4 times 3 times 2, 24q plus 9. So I know how we're going to deal with this, but clearly you should see that 9 is equal to 1 mod 4. Now the way that we can deal with that even better is if I split that up into 16q squared plus 24q plus 8 plus 1. And you can see we can pull a single 4 out. I could actually pull an 8 out, but let's keep the 4 because that's what the proof is going for. Plus 2 plus 1. So I have 4 times another plus 1, and that's equal to 1 mod 4. So I've done it for each of the 4 cases, and we're done with the proof. Oh, before I close out of this video, for the next weeks, you're going to have to pick up a note sheet for those notes, so don't forget that before you go and start the notes.